So we were looking at a confusion matrix, which is a comparison of predicted classes and the given classes and the actual classes. Okay. So accuracy, we saw that total number of true positives plus total number of true negatives divided by total number of total population, right? So it is correct prediction of cat classes, correct prediction of dog classes divided by total number of predictions my model did, or total number of inputs I gave. And next is precision. Precision is how many times my model said it was a cat divided. Uh, Precision is how many times my model correctly predicted cat divided by total number of times my model said it's a cat. Okay, so based on on the previous example, 40 times 20 plus. So these are all my, when my model says it's a cat. 20, it's all too bad now. Okay, suppose, so we have, like, let's say this is 20, this is 40, this is we have 30, this is we have 10, right? So my precision is going to be total number of positives divided by total number of prediction positives. So 20 plus 40 is the total number of times my model said that this picture is of a cat. Out of this 60 times, only 20 times it was correct, right? So my precision is 20 by 60, which is 1 by 3, right? Now precision for negative class will become the same thing, so you can also call it false omission rate, right? So these two things are same only, but when we generalize it over multiple classes, we give it a different name. So basically it means same thing, false negative upon total number of negative. How many times the model says it's a dog, so basically if you find the precision for dog class, you will find that 30 by 40, so it's 75%. So for our given model, the precision for the dog class is a lot better than the cat class, because the model says 40 times it's a dog, but out of them 40 times, 30 times it is correct, 10 plus, right? So the precision is great. Next, what is the recall? So recall is I showed them 50, so the total is 50, right? 50 50, right? So how many times, because 20 plus 30, so in actuality there are 50 cat pictures which I showed to the model, but my model said only 20 of them are cat, right? So true positive becomes true, precision becomes, sorry, recall becomes true positive divided by condition positive, right? So my model said, my model said, I showed 50 pictures to my model. Out of the 50 pictures, out of the 50 actual cat pictures, my model was only able to tell that 20 of them are cats, and 30 of them my model said dog, right? So for these 50 pictures, 20 times my model said yes, it's a cat, and 30 times it said it's a dog. So my precision, my recall becomes 20 by 50. For the dog class, my recall becomes 10 by 50, right? So because we are making more wrong predictions for the dog class, right? So these are the different terminologies which are used to define the or evaluate the performance of a classification model, right? So the main point to remember with the confusion matrix and the various calculated matrices is that they are all fundamental ways of comparing predicted values versus the true values. So basically the confusion matrix, what it does, it compares predicted values with the true values, right? So what constitutes good metrics will really depend on the specific situation. Now this thing will depend on a, so whether it's a good matrix or not, it will depend on the specific situation. So for our case where our model is only predicting based on a picture whether it's a cat or a dog, then it's of course this is poor, because out of so first of all, the total accuracy is very less, 20 plus 10 divided by 100, 30% only. Next, we see that there are more wrong predictions than correct predictions. So these are wrong predictions, these are also wrong predictions. So these are 70 and my correct predictions are 30, right? So model is already wrong. Now suppose this is of a corona test, a diagnostic test which should tell me whether we will get corona in the next 2 weeks or not. Then this metric may become different, right? So it may say that there are 20% chances of getting affected with corona, or 30% based on my model. So the meaning of these classes and all these matrices will change depending upon the condition, right? So basically if I'm just figuring out whether for the corona positive case, because for corona negative I don't worry, so I will be focusing on this class only. So whatever metric I get here does not bother me, because this class is the corona negative class if my data is of classification between corona positive and corona negative, right? Like that. Right, so you can also go through the Wikipedia page, but you will find the same thing only. It's kind of very good to just look at the Wikipedia if you are learning anything new, right? So now how can we say that what's a good enough accuracy, right? So it all depends on the context of situation. So whether 30% is good, 40% is good, 80% is good. So if you talk about therapies or surgery, cancer surgery, so here the probability of success is 20-30%, 5%, but people still want to go it for. So it's not like that only accuracy of 99% is good. So it depends on what situation are you looking at, right? So if suppose we are talking about cricket, if a bowler takes a wicket in every over, then his precision is really good, right? But still it is what 20% only. So out of 6 balls he takes 1 wicket, so it's about 1/6, right? So the accuracy is still less, but it is good because the context here is a game, cricket, right? So he cannot take 6 wicket in 6 balls. Okay, no, I will take only those bowlers who will take 100% wickets, whose accuracy is 100%. No, for like 20-15% is really good, right? If we are judging a bowler based on the accuracy or depending on the context. Okay, so if the model is created to predict the presence of a disease, is the disease presence well balanced in the general population? So for all these things we need to look at whether our data is balanced or not, because our model will be learning from the training set, from the training examples. So those examples should be very well mixed, so all the classes should be balanced, right? And the number of examples should be enough, right? So often models are used as quick diagnostic tests to have before having a more invasive test getting so suppose we are going to test for corona, right? Because it's trending these days. So now in general, if you're talking about some diagnostic tests which are due for prediction of some disease, right? So if I do a normal corona test, swab testing test, so it is done in 20 minutes, I get yes or no. But I want to be really sure, then I can, if I get a yes from the swab test, then I can go for a RT-PCR test or a better improved test to just double check my understanding, right? So now if I go through, if I go talk about cancer testing, right? So some basic urine or a blood test can detect the presence of some kind of a cancer cells or not, right? And based on that prediction, the person need to go into a further radiology or a chemical test, which is kind of costly, which can be costly and can also be uh, important for can also be taxing on the body, right? So suppose you get on a test that yes, you have cancer cells and you have to go to a radiology is like costly, you are paying 2-3 lakhs rupees only to know that you do not have cancer cells. That was a false positive, right? So we want to avoid such situations where any wrong prediction can lead to any kind of worse situation. Worse situation, like you tested positive on a simpler test, then you went on to spend 2-3 lakhs rupees for a comprehensive test just to know that you do not have the disease, right? So we want to be very sure in kinds of uh, the test or the context that we are using our classification for, right? So we need to consider what is at stake. We often have a precision recall trade-off. We have seen that we need to decide if the model we should focus on fixing false positives or versus false negatives. So basically we will try it. So in most of the cases, based on our requirement, we will try to just improve any one of the classes. So if you're talking about disease prediction, we will just focus on the performance of fixing false positives, right? So I don't want okay, so if I go for a corona test and my model should say I have corona, I do not have corona, so I do not have corona should be very less, and I have corona should be given more importance, because that is what I'm looking for. If you do not have corona, then it's not a problem, right? It's probably better to go in the direction of false positive to make sure we correctly classify as many cases of disease as possible. Okay. Yeah, so basically in general, when you will be working on in a company on and building a model of your own and you are testing its performance, so you will be not performing these things in a vacuum. That means you are doing the modeling by yourself without understanding the data is not going to happen. So it is going to be a collaborative process where we should consult with the experts of the domain, right? So if I am working in a healthcare domain, I am analyzing this cancer data based on some blood test reports of like hundreds and thousands of patients, then I should be in constant touch with a doctor who can help me out to understand the parameters, right? Now we will do the same thing. How can I evaluate the performance of a regression model? Regression is where my outcome, my output, or my y variable is a constant, is a continuous real number, just like price or height or weight. Okay, just give me a second. Right. So here my values are going to be real numbers, right? So it is not going to be yes, it's a cat or a dog, whether do you have corona or are you corona positive or corona negative, but it's going to be what is the price, what is the height, what is the height of your son based on the height, based on your height, what should be the price of a house based on the location, the BHK and all that. Okay, so yeah, so regression is a task when a model attempts to predict continuous values, unlike categorical values, which is classification, right? So you may have heard of some evaluation matrices like accuracy and recall. These sort of matrices aren't useful for regression problems. We need matrices designed for continuous values. So accuracy and recall are useful when my outcome is like correct or not, whether it is this or that. But in our case, when we are talking about continuous values, this thing does not work, right? So for example, attempting to predict the price of a house given its features is a regression task. Okay, I'll tell you, okay, 2 BHK in Kormangla or 1500 square foot, what will be the price? So I will get a price. I will not say it, the outcome is not a good house or a bad house or like something like that. So it's a price. So price cannot be accurate. So it is going to be we will be using a term error. Attempting to predict the country a house is in given its feature would be a classification task, right? So basically if the question is like that, so house has a garden, the house roof is kind of a hut shaped, it's a cottage, and I am asking guess in which country this house is located. So when my outcome is the country in which house is located, it becomes a classification task. When I ask based on the features what is the price of the house, then it's a regression task, right? So when it's a regression, so basically I will so my prediction is what y hat is maybe say 5 lakh and y actual is 4.5 lakh, right? So I can just clearly take a difference. Okay, my model is 50,000 off, right? So so the evaluation matrices for regression will be mean absolute error or mean is squared error or root mean squared error, right? These are some simple mathematical terms that we have seen in our older classes, school time, right? So mean absolute error is that this is the mean of the absolute values of error, right? So suppose I have a model which is predicting for n houses what is the price, right? So this is the prediction, this is the actual value. So I will take all the actual minus predictions, remove the sign and add them or take an average of them, because it's a mean absolute error. Error is what? Actual minus predicted. Absolute means remove the sign, right? Without sign, plus, minus or plus. Mean means take the average. So you find this thing for all the individual houses, for n houses, divided by number, add them and divide by number of houses. Okay, now we are, so error is enough. We could have just taken this difference and based on this we have tried to evaluate the performance of our model. But why we are using, we need all these three, or why like this is not good, why this is good, or something like that. So MAE, mean absolute error, won't punish large errors, right? So all these, so basically there are 4 examples of different kind of data distribution where the mean absolute error is exactly the same. Okay, so for this kind of distribution, this is the mean absolute error, right? For this kind of distribution, this is the error that we are getting. For this distribution also we are getting the same line. So basically if we are just judging mean absolute error, then we are not able to kind of capture the complete incompleteness, how my model is performing. We are not able to capture that, right? So all these data look very different from each other, but we are getting the same mean absolute error, right? So basically for this value, which is, we clearly see that it is off, by a good margin, but still my mean absolute error is not doing anything to punish this. Punish means to take it into special consideration, whether to involve it in the data set or remove it, or why it is different. It is not doing that, right? So we want our error matrix to account for these abrupt changes, right? So that's why we take the mean squared error. Now if any error is huge, then if I square it, becomes very high, right? So mean squared error is just you take the actual minus predicted, you square them, add them, divide by total number of total number of predictions, right? So it's just a square of the mean error, right? Larger the errors noted, more than with MAE, making MSE more popular, right? So basically if I get very high MSE, that means that MSE is really high. That means that I have some some values which are way off from my actual prediction, right? So if so suppose my error is 2, MSE will be 4. If my error is 6, MSE will be 36. If my error is 100, my MSE will be 10,000, right? So I am getting very high MSE. That means some of the values are actually getting off, or there are very something different happening with my data. So some of the values are really off. So what can I do is, like, I can give some special treatment to these specific values which have very high error, or I can just completely remove them from my analysis, because they are kind of going. So if I remove this value, my error is good only, right? But if I include this data value, just like this example, if I include this, so just because of this one data point only, I am getting this line. If I remove this, then my line will be going through like this, right? So this is going to be a better prediction, better model, right? Then now the problem with MSE is that mean squared error, the value of my error will be in squared of the units also. So if I'm talking about price, so MSE will be 10,000 rupees square, right? Because it's a squared error. So this thing is a rupees. If you square them, so the answer will be in square. So it's difficult to interpret. So if I say, okay, I'll give you 500 rupees square, bring me a bike. So you cannot interpret this. This does not make any sense. 500 rupees square does not mean anything. So 500 rupees means something, 5 rupees means something, 5 rupees square does not mean anything. So just to be very consistent with the units, we are introducing root mean square error. So same thing, we will find actual minus predicted, we'll square them, add them, divide by the number of items, and I will just take a square root. So it is the most popular. It is the only. This is used in all the regression models, MSE, right? RMSE or RMS, root mean squared error. You will see this term also when we start with the machine learning algorithms, right? So most common questions from students is that, is the value of RMSE good? Now again, so what range of RMSE or the error is good? So whether 10 is good, 100 is good, 0.1 is good, what is that? So context is everything. So our context will define. So if my model, suppose yeah, so an RMSE of 10 is fantastic for predicting the price of a house, but horrible for predicting a price of a candy bar, right? So suppose I am building a model of predicting the predicting the price of a house, right? So my model says, or let me just say, so my prediction is what? Same again, 5 lakh. My true price is what? 4 lakh, right? So my error is around 1 lakh, right? So and I took for 10 houses, and the error is around 50,000 to 1 lakh. So it is fine only, because we are predicting the houses. Some of the houses may go up to 15 lakh, 20 lakh, 60 lakh, or even crores, and my model is giving me an error of 1 lakh to 50,000. It is fine. But suppose if I am predicting the price of chocolates, right? So the price of chocolate is what? 100 rupees, and my model is saying what? It is 500 rupees. The price of chocolate is 20 rupees. My model is saying 120 rupees. So when the error here is around of the range 400 and 100 for predicting the price of a thing which is itself is 100 or 500, then this error is very high, right? I hope you understand. So while predicting the price of a chocolate, it is giving me an error of 100 rupees, 400 rupees. It is when the price itself is around 100, 200, 300, right? So my error should be very less as compared to the absolute term we are predicting, right? And it should be corresponding to the context what we are looking at. So whether it's the prediction for house prices, then 10, 20, 30, 40, 50,000 is fine. But when we are predicting the price of a candy bar or a chocolate, then it should be really less. And suppose if my model is giving what the price of chocolate is 100, my model says 95. The price of chocolate is 150, my model says 145. Then my model is correct because it is giving me just 5 rupees of error. Then this model is good. Right, so compare your error metric to the average value of the label in your data set to try to get an intuition of its overall performance. Average value of the label. So my label is price, right? So my error, whatever my error is coming in 50, 40,000, I will take the price of all the houses, take an average. So my average comes around to be what, 20 lakhs, and in front of 20 lakhs, 50,000 is very, very less. So it's fine. Here, so if in the case of a chocolate, my error was what, 100 rupees. And if I take the average of all the prices, it is coming to be 200 rupees. Then it is very wrong. My error is coming 100 and the average of the prices of all the chocolates in my model is 200. Then this model is wrong. This is a very bad prediction. Okay. So domain knowledge also plays an important role here. So like in any data science or data analytics part, any data analytics job that you'll be doing, you always have to stick to and learn the domain knowledge, right? So where the data is coming from, what is the data about, right? If you are working on the in automation industry where you are trying to predict the comfort level of a car based on the parameters, right? AC, seating, leg space, all that, Wi-Fi, internet facilities, mileage of a car. So you need to understand how these things affect the actual customer experience. So you need to talk to the people in the factory or the people in the managing the customer experience department of the factory. Okay, so context of importance is always necessary to consider. Okay, we may create a model to predict how much medication to give, in which case small fluctuations in RMSE may actually be very significant, right? Suppose we are predicting what kind of dose to be given for a specific kind of fever. So if your fever goes beyond 99, then you should give 100 mg. If it is beyond 102 degrees Celsius, it will Fahrenheit, it will be you should 200 mg, like that. So when the context is devising medications or something related to a disease prediction, then the error can be, RMSE can be very significant. Okay. Yeah, correct. So I think this cool. So like we have now completed the evaluation of classification task. We have completed evaluation of regression task. We have looked at confusion matrix. We have looked at different kind of errors in case of a regression task. We have looked at overfitting, underfitting. We have looked at the process flow of a supervised machine learning method. Right now we start with unsupervised machine learning. Right. So unsupervised learning is that we have data, but we do not have labeled examples. Okay, so we do not know how the data to be classified or whether this should belong to which class. It's kind of we are figuring out ourselves. There is no dedicated label to the examples. Okay, so we have covered supervised learning where the label was known due to historical label data. But what happens when we do not have historical labels? Right, so there are certain tasks that fall under unsupervised learning. We want to do clustering, we want to do anomaly detection, we want to do dimensionality detection. So clustering is grouping similar things together, right? Anomaly detection is finding out the odd one out in a collection, in a data set. Dimensionality detection is that I have multiple features, right? Multiple parameters on which my model depends. Can I reduce them to fewer numbers, right? To make it more understandable and easy to work with. Right, so clustering is grouping together unlabeled data points into categories or clusters. Okay, data points are assigned to a cluster based on similarity, right? So this categories we do not know, we based on the data we try to figure out ourselves. Okay, so suppose I am giving you are analyzing data from of like corona patients, right? So based on based on some random parameter, you can try to club them together. So someone got corona, he got so you have data like a person who is corona positive, right? So he has corona and in number of days he got fine. So he got corona. Yes, he is positive, corona positive, and we are looking at how many days the fever went. So 10 days. Corona positive 20 days. My corona negative 3 days. Right. So something like that, we can club these all sorts of data into 2-3 classes, like whether it is taking more than 2 weeks, 14 days, and less than 14 days. Right. So there is no prior information. Okay. And based on this, we can try to figure out, okay, whether in this case the corona was severe, or in this case the corona was non-severe, or what is the age group of these persons. So we can do further analysis, but initially we try to segregate or group data based on some similarities, which is not explicitly mentioned. So there is no Y label over here, right? We are just looking at data and try to figure out underlying features without any previous historical examples. Anomaly detection attempts to detect outliers in a data set. For example, fraudulent transactions in a credit card. Right. This is anomaly detection. Dimensionality detection is a data processing technique that reduces the number of features in a data set, either for compression or to better understand the underlying trends within a data set. Okay. So yeah. So unsupervised learning, it's important to note these are situations where we do not have correct answers for historical data, which means evaluations is much more harder and more nuanced, right? So we do not have examples, so it is not like we can just look at the examples and learn it. Okay, if this is the input, this should be the output. This is the input, this should be the output. We do not know that. So there is only input. The output we have to figure out ourselves. Okay, how can I divide or cluster or group the data so that it helps us to understand the better understand the situation better, right? So this is the process flow of unsupervised learning. So we have data acquisition, we have data cleaning. These are same steps as before. Then here I do not have a testing and training split, right? No test, train, split. Why? Because there are no training examples here. There are no examples. So I just directly go to model building and training. Then I have transformations. Transformation means whatever I learned from here, I will transform my data. So initially I had just rows of patients. Now my transformation will be who took more than 14 days to recover, who took less than 14 days to recover. This is my, so this data is now grouped into these two categories based on whatever we learned. Then finally, if it is okay, we will do model deployment, right? So I guess this was just a little introduction to unsupervised learning, right? And now we have seen the general process flow of machine learning process, right? How can I evaluate my machine learning algorithm? Okay, and how can I improve training of my model and avoid overfitting and underfitting, right? So now from the next class, what we will be going to do is that we will take one machine learning algorithm or a technique at a class in a single class, right? Each class we'll be looking at a different technique. We will try to understand the math behind it, and we will also look at how can I implement that particular machine learning model using Python, right? So this is it for today. From next class, we will start with linear regression first. Then we'll go on to logistic regression, then decision trees, random forest, and finally support vector machines. So we will be looking at 5 or 6 generic, mostly used machine learning techniques. We will understand the math. We will perform some real analysis on some real data set, and we will try to build our own model and evaluate its performance, right? So thanks a lot.
Okay, sir.
Yeah, we will meet.
Thank you, sir. Have a good day. Good
Yeah,
night.
thank you, Shashi.
Sure, sir. When are we meeting again, sir?
Probably let's meet tomorrow or day after tomorrow. Okay.
Okay, sir. Fine, sir. Fine, sir.
Okay.
Bye, sir. Have a good day.
Bye-bye.